All right, let's look at an appendix. Let's look at Appendix A.6 and talk about what the real numbers really are within reason for a class at this level. Okay. When we're dealing with limits, first topic of Calculus 1, knowing what the real numbers really are is a big deal. Knowing that they're a continuum is a big part of the story of calculus. What a continuum is, a bit of a complicated story. But let's go through this. If you don't grasp every little nuanced detail from this appendix, you'll be okay. But it's certainly worth your time to go through and listen to me ramble on for a little while. So in this appendix, we attempt to rigorously define the real numbers. This is normally a topic from a senior level analysis class. I've got a couple of sections of notes posted on exactly this kind of thing. This is a foundational part of a calculus and analysis. Maybe not entirely essential for the understanding of Calculus 1, but worth your while to go through it and give it a shot. I tried to make it as tangible as I can. We'll state the definition of the real numbers in terms of several axioms. We'll have algebraic axioms. You'll be most unimpressed with those. They're also called field axioms. They give the existence of certain numbers. They tell you how addition and multiplication interact. We'll have order axioms. You won't be very impressed with those either. They talk about the ideas of greater than and less than, greater than or equal to and less than or equal to, which you're familiar with. No surprises there. And the completeness property or the completeness axiom. It's this completeness idea that makes the real numbers a continuum. So we'll spend most of our time talking about completeness. To get this out on the table, the real numbers satisfy the following algebraic properties. Excuse me, let me refresh this. I think I got an O version here. Okay, whoops. Real numbers satisfy the following algebraic properties or axioms by definition. When I say real numbers, these properties hold because they're part of the definition of the real numbers. We have associativity of addition. That is, A plus the quantity B plus C is the same as A plus B plus quantity C. You can add the B and C first, or you can add the A and B first. Doesn't matter, same real number. You can add things in different orders. A plus B is the same as B plus A. That is, you have commutativity of addition. There exists a real number denoted with this thing here. We'll call it 0, such that A plus 0 equals A for all real numbers A. This 0 thing is called the additive identity. So there exists 0 because it's part of the definition of the real numbers. For any real number A, denoting the real numbers, with this symbol here, there's a number B such that A plus B equals 0. Or in other words, there exists a number B such that A plus that number B equals the additive identity, which we've called 0. This is an additive inverse. A has an additive inverse. All real numbers have additive inverses. This is the fourth axiom of addition. They've numbered these with M's. These are multiplication properties. Multiplication's associative to A times the quantity BC is the same as a quantity AB times C. You can do the multiplication of the B and C first or the A and B first. As long as the same three numbers are there, you're okay. Commutativity of multiplication. A times B equals B times A. Order doesn't matter with multiplication, just like with addition. Very unimpressive things. You've probably not seen properties that violate these, but you will. If you've done matrix multiplication before, it's an example of something that's not commutative. So it may seem naive to have to go through all this stuff here, but we've got our reasons to build up these ideas. There exists a real number that we're going to denote with this symbol called 1, such that A times 1 equals A for any real number A. 1 is called the multiplicative identity. So we're guaranteed a 0 and a 1. I told you we were told about existence of certain numbers. So those two numbers are the only ones explicitly required in the field axioms. For each number, non-zero, each non-zero real number A, there's a number B such that A times B equals 1. So B is the multiplicative inverse of A. It's the reciprocal of A. It's probably how you're used to thinking about it. Oh, and we've just said right there, only applies to non-zero numbers. So in a field, there's no such thing as division by zero. There's no reciprocal of zero, if you like. That's a mathematically meaningless concept. And finally, an interaction of addition and multiplication. They label it with a D because it's distribution. A times B plus C is the same as AB plus AC. For all real numbers, A, B, and C, distribution of multiplication over addition. So there's the algebraic properties, the field axioms of the real numbers. Any algebraic structure satisfying these things is called a field. You know any examples of fields other than the real numbers? Rational numbers satisfy all that stuff. With the complex numbers, they satisfy all of those properties as well. Rational numbers usually denoted with a Q for quotient, complex number with a C. So backbone C here. So we can't stop there. We need more properties because hey, those field axioms don't define a unique structure. There's a bunch of different numerical structures that form fields. The real numbers satisfy the following order properties. So here's the greater than, less than stuff, and these are called the order axioms. Again, not terribly impressive, but we'll go through it once and we'll have the real numbers defined. For any real numbers A and B, either A is less than or equal to B or B is less than or equal to A. This is called comparability. If A is less than or equal to B and B is less than or equal to A, then we have A equals B. It must be the same number. This is sometimes called a law of trichotomy, maybe combined with property O1. If A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. Transitivity of inequalities. How inequalities interact with addition. If A is less than or equal to B, then A plus C is less than or equal to B plus C. Preservation of less than or equal to under addition. Multiplication. If A is less than or equal to B and 0 is less than or equal to C, in other words, C is non-negative, then A times C is less than or equal to B times C. Preservation of less than or equal to under multiplication by non-negative numbers. From this, we could prove, let's not, but we could prove that if C is negative, if C is less than 0, and you multiply, then you have to reverse that inequality, as you know. A field that satisfies the order axioms, so a structure that satisfies everything we've listed so far, is called an ordered field. The real numbers are an ordered field. The rational numbers are an ordered field. Complex numbers may be a little surprising. They're not an ordered field. They're a field, but they're not ordered. Check out some notes. Actually, don't bother. I made these for a graduate level class, but I've got some notes online that demonstrate that the complex numbers can't be ordered with a greater than, less than, the way the real and the rational numbers can. So if we look at ordered fields, well, we still don't have it tied down to a single thing because the rational numbers and the real numbers are both examples of ordered fields. So we need something else. I can probably foreshadow it by asking you, what do you think the difference in the real numbers and the rational numbers is? There's rational numbers and there's irrational numbers. Those make up the real numbers. So in a sense, the rational numbers as a collection of numbers on the real number line, they got holes in it, like a hole at the square root of 2, for example. Square root of 2 is an irrational number. And the real numbers form a continuum. So we need to deal with this continuum versus a structure that has holes in it. And we'll do that with the final axiom, the axiom of completeness. But we need the definition first. Consider the following. So sit tight. This is pretty technical stuff, but we'll illustrate it with a story about airplanes taking off. A number m is an upper bound for a set of numbers if all numbers in the set are less than or equal to m. Makes sense. Upper bound. Everything in the set less than or equal to this upper bound. M is a least upper bound for a set S of numbers if it's an upper bound for the set and no other n, strictly less than m, is also an upper bound of S. So they've worded it as it's an upper bound for which there's no smaller upper bounds. It itself is a least upper bound. There are no lesser upper bounds because M is the least upper bound. An example would be consider all negative real numbers. What's the least upper bound? Well, 0. 0 is greater than all negative numbers. 0 is not negative. 0 is not positive. Too busy being 0. So 0 is neither positive nor negative. But 0 is the least upper bound for the collection of negative real numbers, for example. An ordered field is complete if every non-empty set of field elements, which is bounded above, that is, has an upper bound, has a least upper bound. Every set with an upper bound has a least upper bound, is the axiom of completeness. And it's that thing that makes the real numbers a continuum. So the final axiom, if you like, is the axiom of completeness. The real numbers are complete. The rational numbers are not complete. The real numbers are. So we're defining the real numbers to be, as it says here, a complete ordered field. The field part, maybe that word's new to you, but it just set up the arithmetic. The ordered part, you're used to less than or equal to. It's this completeness part that's new to you. I say the rational numbers are not complete. Consider the set S of all rational numbers such that when I square, I might get something less than 2. So we're dealing with rational numbers, and part of the story is they're less than the square root of 2. Now, I can't talk about the square root of 2 as an element of the rational numbers because that's an irrational number. But this set of rational numbers has an upper bound, a rational upper bound, like 3. 3 is rational, and it's bigger than any number that you square and get something less than 2. I can do better than that, but all I wanted was an upper bound. But this set doesn't have a least upper bound. Any candidate rational least upper bound would have to be bigger than the irrational number square root of 2. But then there's another rational number between square root of 2 and this candidate that's also an upper bound for this set. Remember, if we restrict our attention to the rationals, the square root of 2 doesn't exist in that setting, doesn't exist in the field of rational numbers because there's a hole in the rational numbers. Yeah, because they ain't complete. So I can find an upper bound for this set, but you give me any candidate rational least upper bound, and I can find something smaller that's also an upper bound for this set. So your least upper bound, it wasn't least at all. Yeah, but it's because there is no least upper bound because the rational numbers aren't complete. The picture for this is something along these lines. Made it as a dotted line. So here's the rational line versus the real number line, the rational number line. So it's shot full of holes. That's why it's not complete. And that set S was numbers that we square and get something less than 2. That'd be the rational numbers between negative square root of 2 and square root of 2. Now there's a hole in the rationals at negative square root of 2. There's a hole in the rationals at positive square root of 2. There's a hole in the rationals at pi. There's a hole in the rationals at e, the base of the natural exponential and natural log function. There's a bunch of holes in the rational numbers. And that's the reason there's no least upper bound. You pick a rational number. That one right there. You think that's a least upper bound? Well, I can find something smaller that's also an upper bound. And your least upper bound wasn't an upper bound. You can't choose the square root of 2. Now, if I treated this as a set of real numbers, I could choose the square root of 2 because it exists in the setting of the real numbers. But I can't choose it as a rational number. It ain't there. There's a hole in the rational numbers there. It's indicated with a little circle. For the real numbers, I'd choose square root of 2. We'd be good to go. For rational numbers, you can't choose the square root of 2. There's not a least upper bound for that set S of numbers, rational numbers, such that when you square them, you get a number less than 2. All right. So the real numbers are a complete ordered field, and the rationals are not. But maybe there's something else out there? Are there other complete ordered fields? Because when we just looked at fields, we had more than one field, the reals, the rationals, the complex numbers. When we looked at ordered fields, we had more than one. We had the reals and the rationals. And I've kept this in a conversation of things you've seen before in terms of mathematical structures, collections of numbers. Well, maybe there's some exotic collection of numbers out there somewhere that forms a complete ordered field, and it's not the real numbers. Well, in fact, there's not. The real numbers are the only complete ordered field. So the real numbers are the complete ordered field, not a complete ordered field. So there's this uniqueness among complete ordered fields. All complete ordered fields, the math word is isomorphic, iso, same, morph, shape. They have the same shape. It has a very specific math meaning, but that's what the real numbers are, and there's only one such mathematical structure. So saying complete ordered field classifies the real numbers. Our textbook says in this appendix, the completeness property is at the heart of many results in calculus. That's why we're doing this. Without completeness, I say, this is me talking now, without completeness, the existence of limits would not be ensured. Now, you got an intuitive feeling for what a continuum is, and it's really the axiom of completeness that makes the real numbers a continuum. In other words, the real number line, it doesn't have any holes or gaps in it. The rational number line is full of holes and gaps. Got a gap at the square root of 2, for example. Okay, well, I'm sure you're unimpressed with the field axioms and the order axioms. Let's talk about completeness without all this upper bounds and least upper bounds stuff, explicitly at least, in the following little story. So here's a tangible story for you that'll lead to a question, and its resolution is involved with the completeness of the real numbers. So in connection with the idea of completeness and of a continuum, consider the story. Imagine that an airplane taxis down a runway. So it's got height 0, it's still on the ground, and it takes to the air. Once it's in the air, that is, when its height is positive, no longer 0, the plane remains in the air instead of like a basketball dribbling down the runway. Once the wheels are off the ground, they stay off the ground. They don't bounce on the runway a bunch of times. So we make that physical assumption. Also, the plane is either in the air and has a positive height, or it's on the ground. We'll say it's on the ground as long as, say, one of the wheels is on the ground or one part of it's on the ground, in which case the height will be defined to be 0. So if you want to get bogged down in the details, we're measuring the height as a distance from the ground to the lowest point on the airplane once it's up in the air. So that's what I mean by height. This is a conversation to be had about continuous functions and numbers and points. So this is maybe a little awkward, but it makes it more tangible, and you can visualize this story. The plane's not in the air until all parts of the plane are in the air. So the question is there a first point in time at which the plane is in the air? Is there a last point in time at which the plane is on the ground? Is there both of those or neither of those? All right, and this is intimately related to the idea of completeness and the idea of a continuum. So last point in time that the plane's on the ground, first point in time it's in the air, both a last and a first point, part C, or neither of those, part D. So what do you think? So this deserves some thinking time. If we were face to face, I'd poll you and ask the class, what do you think? My experience has shown students like this, like the idea that there's both a last point in time that it's on the ground and a first point in time that it's in the air. But that's a problem. I think this is chosen because people think of the real numbers as distributed sequentially along the real number line. There's a point, and then there's a next point, and then there's a next point. If they were distributed like that, the answer would be part C. There would be a last point in time it's on the ground, and then you jump to the next point, and it's in the air. But that ain't how the points are distributed on the real line. That ain't even how rational points are distributed. Between any 2 points, there's another point. But where was it then? If your answer is part C. Between any 2 real numbers, there's another real number. Where was it? Halfway between that last point in time that it was on the ground and that first point in time that it was in the air. It couldn't have been on the ground because it had already left the ground. It couldn't have been the air because it hadn't gotten into the air yet. The answer can't be both. But that, and I belabored the point because that's a popular choice among Calculus 1 students. That's kind of a popular choice among graduate students. I've been shocked by, in fact. But it can't be, the points aren't laid out along the real line like that. It can't be on the ground and then jump into the air because it had to be somewhere in between. If it was on the ground, as this ain't the last point, it was on the ground. If it's in the air, this wasn't the first point that it was in the air, as is explained in the paragraph. All right, so let's figure out what the answer is instead of what the answer isn't. Let h of t be the function that gives the height of the plane at time t. So in other words, h of t equals 0 for the times that the plane's on the ground, and h of t is positive when the plane is quote unquote in the air. And I'm sneaking in an idea of continuity on this as well, which we'll define in Calculus 1. Consider the set of times that the plane is on the ground with height 0. Let's call it capital T. That'd be the time, the real numbers, where the height was 0. Then capital T, it's a set of real numbers. Think of it as ranging over all times from negative infinity up until when it takes off. The plane eventually takes off, so there's an upper bound on this set. Now getting into the math stuff a little more. But it eventually took off, so eventually it's in the air, and its height is positive, and we've assumed it stays in the air to get the right kind of story, really. So set T is a set of real numbers that has an upper bound. By the axiom of completeness, set T has a least upper bound. Let's denote it T sub L. Okay, so there's what the least upper bound is. You know that point exists by the axiom of completeness. The upper bound guarantees the existence of a least upper bound. Little subscript of a calligraphy L for least upper bound. Since T sub L is the least upper bound for set T, then for all times T less than T sub L, the plane must be on the ground. It was on the ground up to there. T sub L is the least upper bound of that set of times. So time is less than T sub L, plane's on the ground. Time is greater than T sub L, plane is in the air. For all times T greater than T sub L, plane must be in the air with positive height, say. So it's the axiom of completeness that guarantees the existence of this mystery time T sub L. So this is kind of the boundary between when it's on the ground and when it's in the air. The question now is, well, then where is it then? Is it on the ground or is it in the air? If it's on the ground, it's the last point in time that it was on the ground. If it's in the air, then it's the first point in time that it was in the air. Because before T sub L, it was on the ground. After T sub L, it was in the air. Okay. Let's change the notation a tiny bit and draw a picture. Let T star be some particular time, just to give it a different symbol. Suppose H of T star is greater than 0. In other words, at time T super star, the plane's in the air. So it's got some height. Its height is, I don't know, H of T star, positive height. But if it has a height, at some earlier time, it had to be closer to the ground. At some time, say T double star, we must have had the height of the plane is half its current height, say. That's also a positive height. You take a positive number, you cut it in half, you got another positive number. So the story has become something like this. Make the picture bigger, not too big. The plane's on the ground. At some point in the future, it's in the air, and it has some height, some positive height. Well, whatever that height is, earlier, T star star less than T star, earlier, the plane had to be half that high. And it can't just quantum jump up to a certain height. Like I said, implicit in this is an assumption of continuity of the height function. Continuity is something we'll address in chapter 2 in Calculus 1. So earlier it had to have a particular height, say half of that given height. And that's true regardless of what T star is. If H of T star is positive, if the plane is off the ground now, had to be off the ground earlier. That's the point. So there can't be a first point in time where that plane is off the ground, because if it's off the ground, it's got a height. Earlier, it had to be lower, say half the height it is here. So there can't be a first point in time that the plane is in the air. So what's happening at this T sub L time? We can't have H of T sub L be greater than 0 because the plane would have to have been half of H of T sub L, say, earlier, have to be in the air earlier. And it can't be. There can't be a first point in time where that plane is in the air because earlier it was lower. We cannot have the highlighted term. Okay, well, if H of T sub L ain't greater than 0, then it must be equal to 0 because that was the only two choices we had. It was a height. So we must have H of T sub L equals 0. In other words, that's the last point in time that the plane was on the ground. It was on the ground before then, and it's in the air after then. How did we find then? Axiom of completeness is how we were guaranteed the existence of that particular time. So the funny little story of an airplane taking off, the punchline is part B is the answer. There is a last point in time at which the plane was on the ground. And it's related to the very nature, the very definition of the real numbers. Funny little story, if we did this with rational numbers, we can make the answer neither. Because the rational numbers, they got holes in them. I leave it to you to think through that. Let's talk a little bitty bit of history of where this stuff comes from. The axiom of completeness was first stated by Richard Dedekind, lived from 1831 to 1916. And he published this in 1872 in a work called Continuity and Irrational Numbers. Project Gutenberg has a copy of it out there. It's I don't know, maybe 20 pages long. It's not a very long piece of work. Of course, it's a translation, but the original work, I've got a link to it in the notes. Just click on Project Gutenberg and it'll take you to Dedekind's work. He didn't use upper bounds and least upper bounds. He used cuts of the real line. Today, these are called Dedekind cuts. And his approach of using Dedekind cuts is equivalent to the axiom of completeness. So if you want to know who came up with the right idea about continuum and when, it was this guy, Richard Dedekind, in what was the date? Only about 150 years ago, 1872. So it's rather surprising that a rigorous definition of the real numbers really isn't that old. We've been talking about lines since the Greeks in Euclidean geometry, but a clean, rigorous definition of the real numbers only dates from about 150 years ago. The real numbers are a complete ordered field. What a Dedekind cut is a partitioning of the number line into two sets, A and B, such that every element of set A is less than every element of set B. Symbolically, if we take lowercase a number in set capital A, and lowercase b, a set in an element of set capital B, then A is less than B. The sets don't intersect, and you union them, and you get the whole real line. The word partition includes these ideas of disjoint. A intersect B is empty, and A union B gives the whole real line. But that's the conditions, and the axiom of completeness then can be said exactly one of the following holds. There's a largest number in set A, or there's a least number in set B. You know, that's exactly how we had the airplane thing. In the airplane story, we had the plane sitting on the ground form the times in set A. A equals a set capital T, if you like, from before. And when the plane was in the air, those times form set B. And we found out in that case, in that example, set A contained a largest number. It was that T sub L, the last point in time when the plane was on the ground. Now, without the story of the planes, it could be the situation where set B contains a least number and set A doesn't contain a greatest number. That's possible for sets of numbers, but that doesn't fit our story about airplanes. So there's you a kind of an informal idea of what the real numbers really are in terms of what completeness means, and a little story about airplanes taking off. All right, on to the more technical stuff and the more computational stuff and Calculus 1. I can't wait. I'll see you there. Have a nice day.